So we go to now first exercise 1.1. Question number 1 is check whether each of the given relation is reflexive, symmetric and transitive or not. So in the first sub question you are given a set here which is 1 to 14 and relation is given in this way. You know relation means set of ordered pairs here x comma y, where this is the relation between these two variables x and y, and obviously here relation is defined on this set, so x and y both comes from A only. So let's see this first one. So here you can say y equals to 3x. So if for example x is 1, then y will be 3. So if I list the members here, x is 1, y is 3, so 1 comma 3. Next if I take x2, then obviously y will be 6. Next if I take 3, it would be 9. Next if I take 4, for example, it will be 12. Now I cannot take x equals to 5. If I take 5 here, then y will be 15, but 15 is not member of this set. This is up to 14. So we have this many members in R. Right? Remember, 4, 5, 15 will not be member of the relation set R. Why? Because 15 is not member of this. So relation R has this many ordered pairs. This you know even from 11th standard. This is called the representation of the relation by roster form or listing method. Now first property, reflexive. So is it reflexive? The answer is obviously no. It's not reflexive. Not reflexive. Why? When the relation is said to be reflexive, for every member of the set 1 1, 2 2, 3 3, 4 4 up to 14 14 all should be there in the relation set, but here none of them are present because 1 comma 1 is not in R, even 2 comma 2 is also not in R, and so on. This much is sufficient. Reflexive means 1 1, 2 2, 3 3 all should be present in R, so this is not reflexive. Second one, you can observe directly. Second is symmetric property. Is it symmetric? So answer is no. 1 comma 3 is there, but 3 comma 1 is not there, so you are through. So not symmetric. This is not symmetric. You need to give the proper reason why it is not symmetric. Reason is 1 related to 3, but 3 is not related to 1. 1 comma 3 is a member of R, but 3 comma 1 is not a member of R. Remember, one example is sufficient. If you want one more, 2 related to 6 because 2 comma 6 is in R, but 6 is not related to 2, and so on. Many examples you can find, but this much is sufficient. Third one, what do you think about transitive property? You need to take one common member here. 1 comma 3 is in R, 3 comma 9 is also in R, but you look at it 1 and 9 which is not there, so not transitive. So not transitive. This not transitive. What's the reason? Because here 1 related to 3, 1 comma 3 is a member of R, 3 related to 9, 3 comma 9 is also member of relation set R, but 1 related to 9, 1 comma 9 is not there in R. Therefore one example is sufficient, therefore it's not transitive. So this way you need to justify whether it's reflexive or non-reflexive. You need to give the proper reason. 1 comma 1, 2 comma 2 all are not there in R, not reflexive. Symmetric means reverse should be present, but here reverse is not present. One example is sufficient to show that this is not true. Not transitive, one example is sufficient. This and this both are present, but this is not. 1 comma 3 is there, 3 comma 9 is there, but 1 comma 9 is not there. So therefore not transitive. So you can say that this is not an equivalence relation. Not an equivalence relation. It's not asked, but just for your information I'm telling you. Not an equivalence relation. You know, equivalence relation means it should be reflexive, symmetric and transitive. Go to second sub question here. This was the first sub question. Their relation R is given in this way: x comma y, where y is equal to x plus 5 and x must be less than 4. This relation is defined on natural numbers, on n, you know, set of all natural numbers. So these x and y both will come from n, but x should be strictly less than 4. So there are only 3 possibilities for x, 1, 2 and 3. So if I write the members of the relation set R, if I take x1 here, 1 plus 5, y will be 6. If I take x equals to 2 here, then 2 plus 5, 7. Next, if I take x equals to 3 here, 3 plus 5, 8. Only you have 3 ordered pairs. You are given that, remember, x is less than 4. And relation is defined on natural numbers, on n. So we have just 3 ordered pairs. Now, just by observation, you can see that clearly not reflexive. Clearly not reflexive. Why not reflexive? Because if it is on n, then 1 1 2 2 3 3 4 4 all should be present. Reason: because 1 is not related to 1, 2 is not related to 2 and so on. 1 is not related to 1 means 1 comma 1 is not in the relation set. Not symmetric also, which is obvious. Why not symmetric? Reason is 1 6 is there, 1 related to 6, but 6 is not related to 1 and so on. And not transitive also. Will it be transitive? Let's see here. So third property here, which is transitivity. So what usually we do in transitivity property, we take first ordered pair here, for example 1 comma 6. Now do you have any ordered pair having 6 at the first place? No. Go to second ordered pair, 2 comma 7. Do you have 7 at the first place in any other ordered pair? No. So for this you cannot check. 3 comma 8. Do you have any ordered pair having 8 at the first place? No. So for these also you cannot check. So in this case we say that this is transitive relation. I repeat, when we say that not transitive, remember, this is very important case. Not transitive means I'm writing meaning of not transitive relation. Not transitive means you must have a comma b, b comma c, then a comma c should not be in the relation. Then it is called, this is in the relation, this is also in the relation, but third ordered pair is not. If this happens, then we say that this is not a transitive relation. But we don't have such case here. You see 1 comma 6 is there, but there is no ordered pair having 6 at the first place. So in this case you cannot check. 2 comma 7 is there, but do you have 7 comma something? No. So in this case also you cannot check. 3 comma 8 is there, do you have 8 comma something? No. So in this case also you cannot check. So you don't have 2 ordered pairs which are in the relation, but third one is not. If this happens, then not transitive, but here we don't have such case in these 3 ordered pairs, so we say that this is a transitive relation. So now next definition is relation R, where definition is y is divisible by x, and on this set it is defined. So set on which relation is defined 1, 2, 3, 4, 5, 6. Now first property, reflexive property. So every time it's not necessary list all ordered pairs. You can say directly also, like here for reflexive property, if I take 1, can you say that 1 is divisible by 1? Yes. So 1 related to 1, because 1 is divisible by 1. 1 is divisible by 1. So you can say that 1 related to 1. Then for reflexive property, you are checking for itself, remember. Can you say that 2 is divisible by 2? Yes. So 2 related to 2. And so on, 3 also related to 3. Why? Because 3 is divisible by 3. In general, you know, every number is always divisible by itself as soon as it is positive. So for every x in A, you can say that x related to x. So therefore relation is reflexive. So R is reflexive. R is reflexive. This is the reflexive property. First one. If I put 0 here, then this will not be reflexive because 0 doesn't divide 0. But as far as positive and negative integers concerned, you can say that this is always the reflexive relation. 1 divides 1, 2 divides 2, 3 divides 3, 4 divides 4, 5 divides 5. So it's always true. So it's a reflexive relation. But if you go to the second property, here you can say that, for example, 1 related to 2. Why? Because 2 is divisible by 1. 2 is divisible by 1. Now you do the reverse, but 2 is not related to 1. Why? What's the reason? Because 1 is not divisible by 2. Remember. So therefore, what's the conclusion? Not symmetric. Not symmetric. You can find many examples. For example, you can take here 2 related to 6, because 6 is divisible by 2. But 6 is not related to 2 because, 2 is not related to 6 because 2 is not divisible by 6 that way. One example is sufficient. So this is reflexive but not symmetric. So here under divisibility, for example, you can say that 1 related to 2 because 2 is divisible by 1. You can take 2 related to 4 because 4 is divisible by 2. Then 1 is also related to 4 because 4 is divisible by 1. One more if I take, for example, here 1 related to 3 because 3 is divisible by 1. 3 related to 6 because 6 is divisible by 3. Then this is also true. 1 related to 6 because 6 is always divisible by 1. You drop this count. So every time this holds, even if I take one more, for example, 3 related to 3. Every number divides itself. 3 is divisible by 3. 3 related to 6 because 6 is divisible by 3. Then if I take this 2, this is also true. 3 related to 6 because 6 is divisible by 3, and so on. So this is always transitive relation. Remember, this is a transitive relation because as this here, for every x, y in a set A, whenever x related to y and y related to z, then x is always related to z. This is always true. So this is a transitive relation. Next example, if I go to fourth here, example number 4. So in the fourth example, you are given a relation R here as x comma y such that x minus y is an integer. It should be an integer. Answer should be an integer. On z. Z means all integers, you know. So this is infinite relation. You cannot list all ordered pairs. It's not easy. So directly we answer. So first property. I again explain the relation. When we say that this is a member of the relation set R, if the difference is an integer. The integer could be anything on Z. Now Z has infinitely many members, so R can have infinitely many ordered pairs. So it's difficult to list all ordered pairs, so we answer directly. Now first, reflexive property. So what do you think about reflexive? You need to see 1 minus 1, which is 0, which is an integer, is an integer, you know. This answer should be an integer. So therefore, you can say 1 related to 1. 2 related to 2? Yes, because 2 minus 2 is also an integer. Can you say 3 related to 3? Yes, because 3 minus 3 is also an integer. Can you say 100 related to 100? Yes, because 100 minus 100 is also an 0, and which is an integer. Can you say minus 2 related to minus 2? Yes, because minus 2 minus minus 2, which is also 0, and it's an integer. So because of this, every member, in general you can say that for every x in Z, x is related to itself. So therefore this relation is reflexive. Because of this it turns out to be reflexive. Now recall what is symmetric properties. If you have A related to B, then show that the B related to A. If this is true, then it is called symmetric. Now I'll start with this. Let A related to B. What is the meaning of this as per definition? A minus B is an integer. This is the definition given to you, remember. Now if A minus B is an integer, then if I take its opposite, that is B minus A, this is opposite of this. If this is 2, then this is minus 2. If this is 4, then this is minus 4. If this is minus 100, then this is 100. E is also an integer. Now what's the meaning of B minus A is integer? You can say that B related to A. And this is true for every A, B and Z. So what you have shown, whenever A is related to B, then B is related to A. So therefore, this relation R is symmetric. This is a general proof, remember, like that. I have not taken any ordered pair. Generally I have given. You can take ordered pairs also. For example, you can show like this also. 2 related to 4. It implies 4 related to 2. Why? 2 minus 4 is minus 2. 4 minus 2 is 2. 3 related to 0. 3 minus 0 is 3. 0 is related to 3. Minus 3. And so on. So here reverse ordered pair is always present. So this is a symmetric. I'm giving various methods to show this property, like this, or you can give like this and so on, as I've shown earlier. Third property, transitive property. Now what is transitive property? You start with this. Suppose you have this. Suppose A related to B, B related to C, and at the end you show that A related to C. This you need to prove. These two things you need to start. With these two things you are going to start, and this one you are going to prove, remember. If I can do this much, you can say that it's a transitive relation. So suppose A related to B here, and B related to C. You have started with this. What I'll do, I'll use the concept and I'll show that A related to C. This one I am going to show with this. Now what's the meaning of A related to B? A minus B belongs to Z, means it's an integer. B minus C is an integer, means it belongs to Z. A related to B, this is given in the question itself that A minus B should be an integer. Integer means belongs to Z. B related to C means B minus C should be an integer, means belongs to that. If this is an integer, this is also an integer. So if I add these two, A minus B plus B minus C, obviously this is also an integer. If this is an integer, this is also an integer. So their addition is also an integer. So it implies BB will get cancelled. You can see that A minus B is also an integer. So if A minus C is an integer, you can say that A related to C. So therefore what you have shown, whenever A related to B, B related to C, it implies A related to C for every A, B, C belongs to Z, remember. So therefore R is transitive relation. So it was reflexive, it is symmetric and transitive. So you can say that it is an equivalence relation. This is not asked in the question, but just I'm showing you for information. This is an equivalence relation. Question number 2, show that the relation R on all real numbers. Remember, this bold R indicates all real numbers and simple R is a symbol for relation. So here definition of R is this a comma b, where the first coordinate should be less than or equal to square of the second one. You are asked to show that it's not reflexive, not symmetric, as well as not transitive. So this question becomes little bit easier because you are directly asked to show not symmetric, not reflexive, and not transitive. So you just need to think for an example for which reflexive property doesn't hold. Try to find an example for which symmetric property doesn't hold, and try to find an example for which transitive property doesn't hold. So let's try for this. So here we give an example for which one member is not related to itself. Reflexive means A should be related to itself. Now here we want to show that not related. So you can take, let's take for example fractional value. If I take 1 by 2, you can say that it is not related to 1 by 2. What's the reason? Because you can see that A is 1 by 2 here, which is not less than or equal to B square, so square of this, which is 1 by 4. Now this is not true. 1 by 2 is not less than 1 by 4. So you can say that 1 by 2 is not related to 1 by 2. I've chosen fractional value. It might be true for integers, but you need to give an example for which element is not related to itself. Remember, you can take any number from R, not necessarily this. One example is sufficient. If you want, you can take some more examples, but here you can say that 1 by 2 is not related to 1 by 2. Why? Because 1 by 2 is not less than or equal to B square, that is the square of 1 by 2, which is 1 by 4. This is not true, therefore this is not related. Second one, not symmetric. For that you can find number of examples, which is not a big task. You can say 1 related to 2. Why? Because 1 is less than or equal to 2 square, which is 4. But 2 is not related to 1, because what's the reason here? 2 is not less than or equal to 1 square, which is 1. 2 is not less than or equal to 1. So here 1 related to 2, but 2 is not related to 1, so not symmetric. Symmetric means reverse should be present. Here reverse is not present. This is one example, and it's sufficient to show that not symmetric. Next one, you want to show that not transitive. You want to show that it's not transitive. So question number 3, you are given this set, which is a finite set, and relation R is defined in this way: A comma B, where B is A plus A, B is A plus 1, sorry. Now this relation is defined on finite set, so you can list out ordered pairs very easily, not a big task. If it is on like this question on R, then it's difficult to list ordered pairs because this is infinite set. But here you can list out. So if I take A equals to 1, B will be 2. If I take A as 2, next member, then this is 3. Next, if I take 3, this is 4. Next, if I take 4 here, then it will be 5. If I take 5, next will be 6. Now I cannot take 6 here, it is there, but it will be 6 comma 7, which is not in R. So up to this you need to take. Now from this, very clearly you can see that not reflexive. Now after doing so many examples, you can see why not reflexive. Because 1 is not related to 1, 2 is not related to 2, and so on. Not symmetric, which is also obvious. Why? Because you can see that here 1, 2 is there, 1 related to 2, but 2 is not related to 1. reverse is not there. What about transitivity? You can see that here transitivity property also doesn't hold, so not transitive. Why? Because you look at first two ordered pairs, 1 related to 2, get ordered pair having 2 at the first place, so you can take 2 related to 3. But you can see that, what about 1 related to 3? 1 comma 3 is there in this? No. So not transitive, not reflexive, not symmetric, and not transitive. So here, next question, relation R equals to A comma B, where A is less than or equal to B on all real numbers. Now here relation is defined on an infinite set, so it's difficult to list all ordered pairs. In previous question, if you look at, in this question, you could list the ordered pairs because the relation was on finite set. But in such questions, it's difficult to list out the ordered pairs. So what I'll do, I'll give direct proof of each of the property or each of the type. Here, this is very standard relation, less than or equal to. And the first property, if you recall, for every real number, you know, real number R, A is always less than or equal to itself. So therefore, you can say that A related to A, and therefore here R is reflexive. There's a standard way of doing this. So here 1 comma 1 will be there. Why? Because 1 is less than or equal to 1. 2 comma 2 will be there. Why? Because 2 is less than or equal to 2. For example, this way. 2 is less than or equal to 2. It implies 2 related to 2. 3 is less than or equal to 3. So 3 related to 3. 0 is less than or equal to 0. So 0 related to 0, and so on. But this is a general method of proving the proof of such types, so it's a reflexive relation. Second, it's quite obvious that 2 is less than or equal to 3, but 3 is not less than or equal to 2. So what I'm trying to tell you is this 2 related to 3, but 3 is not related to 2. And you can find many more such examples. So this is not symmetric. Why? Because of this. As this, you can find many more such examples. One example is sufficient, as I mentioned number of times earlier. Third, transitive property. Recall transitive property. What you need to do in transitive property, you start with these two. A related to B, B related to C. This should be common. And at the end, you conclude that A related to C. If I can conclude this, I can say that the relation is transitive. So we start with this and we try to get this. So suppose A related to B here and B related to C. B, one member should be common. Now what we do at the end? At the end we are going to prove that A related to C. You will realize how. Now this is your supposition, remember. You are going to start with this and you are going to conclude this. Now what's the meaning of A related to B? Look at that definition. A should be less than or equal to B. What's the meaning of B related to C? B should be less than or equal to C. If A is less than or equal to B, B less than or equal to C, you can say that A has to be less than or equal to C. So therefore you can say that A related to C, and therefore the relation R is transitive. So this is transitive, not symmetric, and reflexive. So this is not an equivalence relation.